Welcome, Nocturnal Minds, aboard. Your learning journey starts now. Right, let's dive straight into the deep end with quantum mechanics. Quine famously said, physics has the whole field covered, and most philosophers would nod along. But physicists, they're often wrestling with these philosophical head-scratchers themselves, especially when it comes to what we even mean by reality. The reason for this hesitation, this mealy-mouthed approach, lies squarely in quantum mechanics. It's the theory that predicts everything under the sun and then some, yet it throws up a fundamental difficulty that's baffled everyone for a century. The battleground, where the tiny quantum world meets our everyday macroscopic experience. This is the infamous problem of measurement. As Heisenberg put it, the theory's math is one thing, but describing actual events in plain language? That's where the trouble starts. So back in 1926, when quantum mechanics was largely put together, it didn't really fix the old puzzle of wave-particle duality. If anything, it made it stickier. Think about Young's two-slit experiment, the classic setup. Shine light through two slits, and bam! An interference pattern appears on a screen behind those wavy bands of light and dark. Close one slit, the pattern vanishes. Now, here's the kicker. If you fire photons one at a time, randomly opening or closing one slit, the interference pattern still builds up, spot by spot. It's like each photon is interfering with itself. How can a single particle pass through both slits? Feynman basically called it the heart of quantum mechanics, the only mystery. It's utterly bizarre from a classical perspective. Einstein first pointed out this dual nature of light back in 1905. Niels Bohr, though, took longer to accept it fully. For Bohr, this wasn't a bug to be fixed in the equations. It was a feature, a fundamental limitation baked into the universe by the quantum of action, Planck's constant h. He argued we had to give up the idea that we could explain phenomena completely independently of how we observe them. Since our experiments always involve classical apparatus, classical concepts inevitably creep into our descriptions. Bohr went further, suggesting classical concepts were the only real ones, the bedrock of communicable science. The quantum postulate, he thought, didn't introduce new concepts but placed limits on how different classical concepts could be used together in a single experiment. You couldn't, for instance, simultaneously define a particle's position and momentum with arbitrary precision in the same experimental setup. This limitation gave rise to the uncertainty principle. So, according to Bohr, each experiment highlights a particular aspect of reality using a specific set of classical concepts, and you just don't expect these different sets from different experiments to perfectly mesh together. This, he believed, explained how light could act like a wave in one situation and a particle in another, without any contradiction, because the underlying classical concepts weren't being contradicted, just selectively applied. His big win was showing that these complementary concepts, like position and momentum, truly couldn't be simultaneously pinned down in a single measurement scenario. Take the two-slit experiment again. If you try to peek which slit the photon went through, say, by measuring the kickback of the slit, you inevitably mess with its position too much, and poof, the interference pattern disappears. Bohr kept his focus firmly on the experimental results, the phenomena, rather than getting lost in the complex mathematics of the new quantum formalism. But the real sting of the measurement problem hits you hardest when you look at the equations themselves. In standard non-relativistic QM, the state of a system is described by this wave function, psi. It lives in a high-dimensional space representing all possible configurations of all particles. This psi evolves smoothly and predictably according to the Schrödinger equation, which is linear. What does linear mean here? It means if you have two possible states, psi1 and psi2, that evolve nicely, then any combination like c1 times psi1 plus c2 times psi2 also evolves nicely, where c1 and c2 are just complex numbers representing weights. Now, here's the killer question. Suppose psi1 describes a state where a particle reliably triggers a detector, and psi2 describes a state where it reliably bypasses it. Both are perfectly fine, deterministic outcomes of the Schrödinger equation. But the superposition state, c1 times psi1 plus c2 times psi2, is also a solution. So what happens when we measure? Does the detector click or not? The smooth evolution seems to break down right at the moment of observation. The standard answer, the orthodox view, introduces a special rule. The measurement postulates. It says that this superposition state, C1s plus C2 P2s, is only real before you actually measure it. The instant you interact with the system, something dramatic happens. The wave function collapses. It randomly picks one outcome, psi1, with probability a square or phi2 C2. This is where the famous Born rule comes in, telling us the probabilities. If you repeat the measurement quickly, you'll always get the same result, meaning the state must have genuinely changed after the first measurement. This sudden probabilistic jump from a superposition to a definite state is called wave packet reduction, or WPR. The big issue? This collapse process is completely different from the smooth deterministic evolution governed by the Schrödinger equation. It feels like a fundamental discontinuity in the laws of physics. How does this relate back to wave-particle duality? Well, consider a photon hitting a screen with many regions. Its state might be a superposition C plus C2 P2 plus dots, where psi3 means the photon is localized in region K. When you develop a photographic plate, you measure its position. According to the measurement postulate, you find it in region K with probability C q squared. The spread-out wave function gets magically converted into a single, localized spot. That's WPR doing its job. But wait, maybe this collapse is just an illusion? What if we model the measuring apparatus explicitly? If the apparatus reliably shows outcome K when the system is in state C qua, then the combined system plus apparatus state becomes C qua. By linearity, the initial superposition C1 plus C2 twice plus dots should evolve into fiston plus C2 plus dot no collapse. The same logic applies if we include the observer. It seems like we could keep adding layers, but the problem persists. The chain of measurement has to stop somewhere, and stopping it requires invoking the measurement postulates, not just more physics. This chain-stopping problem was hammered home by John von Neumann, and famously Erwin Schrödinger, with his thought experiment involving a cat. Imagine a cat in a box linked to a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays psi1, the counter clicks, releases the poison, and the cat dies. If it doesn't decay psi2, everything stays fine. The initial state of the whole system, atom plus apparatus plus cat, is a superposition C1 psi1 plus C2 psi2. If we trust the unitary evolution, the final state should still be this superposition. A cat that is both alive and dead simultaneously. When does the cat actually decide? Only when we open the box and look. Or did it decide earlier? Einstein famously asked, "Is the moon there when nobody looks?" If the cat is genuinely in a superposition until observed, then the initial quantum description was incomplete. Why not just look for a deeper, more realistic theory? Von Neumann and Schrödinger hinted that maybe this collapse, this WPR, wasn't just a quirk of quantum mechanics, but pointed to a fundamental boundary of physics, a point where the objective description meets the subjective observer. Wheeler summed it up starkly. No phenomenon is a phenomenon until it is registered. Heisenberg similarly noted the factual element only emerges with the observer. But Einstein had a simpler, more radical idea. Perhaps the quantum state is just incomplete information. WPR isn't about the world changing, but about us learning something new. His EPR argument focused on distant particles A and B prepared in a correlated state. Measuring A instantly tells you about B's state, even if they're light years apart. If the act of measuring A causes B's state to become definite via WPR on the total state, how can B's state change due to something happening far away? That sounds like spooky action at a distance, violating relativity. Therefore, Einstein argued, B must have been in a definite state already. The quantum description was just missing something. Then came John Bell in the 60s and 70s. He looked at the correlations between distant measurements, like in the EPR setup. He derived a mathematical inequality that any theory adding extra hidden variables to quantum mechanics must satisfy, provided those variables are local, meaning they can only influence things nearby. The logic was, hidden variables plus locality implies Bell inequality. But experiments, beautifully conducted by Aspect and others, showed that quantum mechanics violates these inequalities. They match the predictions of standard QM, not the Bell inequalities. What does this mean? If there is a deeper level of reality beyond the quantum state, it cannot be local. It must involve some kind of non-local connection. Interestingly, Bohr himself in his reply to EPR seemed to accept this non-locality. He argued that changing the measurement on one side could affect the probabilities on the other side, even if it didn't allow signaling faster than light. So, whether you believe in hidden variables or not, it seems non-locality is deeply woven into the fabric of quantum mechanics. By the mid-80s, the tide was turning. Experimental tests and Bell's work cast doubt on Bohr's complementarity. Suddenly, a viable alternative, long overshadowed, looked promising: pilot wave theory, also known as Bohmian mechanics. This theory offers a complete realistic explanation for the measurement problem, and crucially, it makes exactly the same predictions as standard quantum mechanics for non-relativistic systems. It's explicitly dualistic. You have the familiar wave function psi, evolving according to Schrödinger's equation, but you also have real point-like particles moving through ordinary three-dimensional space. Their paths are determined by the wave function via a specific guidance equation. De Broglie actually proposed this idea way back in 1927, but it got little traction. Bohm revived it in 1952. Why was it ignored? Partly because extending it to relativistic quantum field theory seemed impossible, as QFT allows particle numbers to change, making a fixed particle trajectory tricky. Also, initially, it wasn't clear how it accounted for the apparent randomness of wave function collapse. So how does pilot wave work? Any complex wave function psi can be written as a times e to the is divided by h bar, where a and s are real functions. The particle's velocity at any point x, t is given by the gradient of this phase function s, v of x, t equals h bar over m times the gradient of s of x, t. This is the guidance equation. Crucially, the probability density rho of x, t equals a squared of x, t. The Born rule is conserved under this flow. The probability of finding the particle in some region flows along with the particle's trajectory. This means the theory reproduces the statistical predictions of standard QM, and it solves the measurement problem elegantly. Nothing weird happens during measurement. You just observe the particle where it already is, following its trajectory. The appearance of wave function collapse, WPR, is explained as an effective phenomenon. When the wave function splits into components corresponding to different macroscopic outcomes, like a live cat versus dead cat, these components decohere, meaning they stop interfering with each other. We pragmatically ignore the other branches because they don't affect our experience. Now, pilot wave isn't without its own issues. There's a slight whiff of epiphenomenalism. The particles seem to follow the wave, but the wave's evolution doesn't depend on where the particles are. It feels like the wave is the main character, and the role of probability remains enigmatic, tied to the initial conditions of the universe. Anthony Valentini has argued that maybe the universe isn't in equilibrium, and this could lead to observable deviations from the Born rule, potentially testable in cosmology or at very small scales. But let's be honest, finding such signatures might be like looking for a needle in a cosmic haystack. Despite these quirks, its appeal is strong. It's a fully realistic theory, doesn't need mysterious collapse rules, and directly challenges Bohr's arguments for complementarity. It explains how we see novelty emerge from underlying structure and provides a concrete mechanism for the appearance of wave function collapse. If realism like pilot wave seems plausible, then Bohr's complementarity really loses its footing. This pushes us towards alternatives. One major class is collapse theories, or dynamical reduction models. These theories propose modifying the Schrödinger equation itself. Instead of pure, smooth evolution, they add a random stochastic process that causes the wave function to spontaneously localize, or collapse, without needing an external observer. The most famous example is the GRW theory by Gherardi, Rimini, and Weber. Imagine the wave function psi occasionally getting hit by a Gaussian spike, localized at some random point q in time t. This makes the wave function sharply peaked around q. The rate of these hits and the width of the localization d are new fundamental constants, chosen so that for atoms these hits are incredibly rare, preserving atomic stability. The probability of a hit happening at q is proportional to the wave function's amplitude squared there. And crucially, this happens for every particle in the system. For a macroscopic object with Avogadro's number of particles, even if individual hits are rare, the collective effect localizes the entire object almost instantly. So, what's the deal with collapse theories? The core idea is simple: ditch the measurement postulates. The wave function always represents a definite distribution of stuff, and its evolution includes a built-in mechanism for spontaneous localization. This naturally solves the measurement problem for macroscopic objects. The big advantage? Philosophical simplicity. No weird dualism, no mysterious trajectories, no epiphenomenalism. Just modify the equations, but there are serious drawbacks. First, the tails problem. Even after a hit localizes a cat, the part of the wave function describing the dead cat is still technically there, just with a tiny amplitude. Is it gone, or is it still a real possibility? This echoes issues in the many worlds interpretation. Second, and perhaps most damning, there's no good relativistic version of these theories. Incorporating them into the framework of special and general relativity would require a massive overhaul of relativistic quantum field theory. That's a huge theoretical hurdle. If all these realist alternatives hit snags, what's left? Does physics itself turn out to be fundamentally confused? Or maybe realism is the flawed assumption? Enter the Everett interpretation, often called the many worlds interpretation. Like pilot wave and collapse theories, it takes the wave function seriously. But unlike them, it doesn't add new physics or postulates. It simply says, the wave function evolves unitarily according to Schrödinger's equation, always. When faced with a superposition leading to different macroscopic outcomes like Schrödinger's cat, Everett says both outcomes are real. The wave function branches into multiple, non-interacting components, each representing a different world. The measurement problem is solved by denying collapse entirely. The big negative, it's fantastic. Too fantastic for some tastes. If every possibility is real, then when you look at the cat, you don't find it definitively alive or dead. Instead, you find yourself in one branch where you see a live cat, while another you find a dead cat. All possibilities are actualized. Everett's original 1957 paper was brilliant. He showed that even without collapse, the unitary evolution naturally leads to observers experiencing definite outcomes. Consider a measuring device with memory. As the wave function evolves, it creates a superposition of the device being in different states, each with a specific memory record. Each of these records is a relative state of the device. The Born rule then acts as a weighting factor over this multitude of possibilities, recovering the standard probabilistic predictions. However, Everett's initial formulation faced hurdles. It seemed to imply consciousness was key, raising questions about why branching consciousness is impossible. More critically, what are the probabilities about if everything happens? If you know all possibilities exist, what does it mean to say one is more likely? And how do we decide which basis defines the different worlds? Is it a live or dead cat? Or some other, more complex superposition? The preferred basis problem was a major sticking point. The breakthrough came with the development of decoherence theory in the early 90s. Decoherence showed that the preferred basis problem isn't a fundamental flaw, but rather an effective phenomenon. Just like wave function reduction in pilot wave theory, the branching into distinct worlds is closely related to the loss of coherence between different parts of the wave function due to interaction with the environment. This happens naturally and rapidly for macroscopic systems. Because branching is an emergent, approximate process, we don't need a perfectly precise mathematical definition of the preferred basis. It's enough for it to work for all practical purposes. This cleared up a major hurdle, but the probability problem remained. Why the Born rule? And what's the right way to think about uncertainty when you know you're in one branch, but which one is random? Defenders of Everett have answers. They argue probability relates to self-locating uncertainty. You don't know which branch you'll end up in. Decision theorists like Deutsch have shown that rational agents must behave as if probabilities follow the Born rule, regardless of their personal preferences for outcomes. So, where does quantum mechanics go from here? The Everett interpretation, despite its explanatory power, remains deeply counterintuitive for many. Given the lack of progress on relativistic versions of pilot wave or collapse theories and the fading credibility of Bohr's complementarity, the outlook is uncertain. Many physicists look towards the frontiers, especially quantum gravity, hoping that unifying relativity and quantum mechanics might resolve these foundational issues. Others bet on future technology, arguing that eventually, experiments will be sensitive enough to distinguish between these realist interpretations, perhaps revealing subtle violations of the Born rule or testing predictions at the quantum to classical boundary. The takeaway for anyone trying to revive a more instrumentalist, anti-realist view of quantum mechanics is clear. They need to convincingly rule out these realist alternatives, not just offer a different perspective. For those wanting to dig deeper into these quantum quandaries, there's a wealth of material. Wheeler and Zurich's collection is essential reading, featuring the classic Einstein-Bohr debates. Valentini and Bacigalupi's book provides context from the pivotal 1927 Solvay conference. For contemporary views, Zeilinger and Bubb offer interesting perspectives. On pilot wave, Goldstein and Valentini explore its nuances, including non-equilibrium aspects. Girardi's entry in the Stanford Encyclopedia covers collapse theories. Zurich, Gell-Mann, and Hartle are key figures in decoherence and the many worlds interpretation. Saunders tackles the tricky issue of probability within Everett. And for broader syntheses, Penrose, Ray, Hughes, Redhead, Pitowski, Maudlin, and Bell's own collected works provide invaluable insights across the landscape of quantum foundations. Having wrestled with the strange and wonderful world of quantum mechanics, let's pivot to another fascinating frontier where similar questions about structure, representation, and explanation arise: the human mind. The philosophy of psychology sits at the intersection of philosophy of science, philosophy of mind, and empirical psychology. While various subfields like psychoanalysis or social psychology have drawn philosophical attention, cognitive psychology and cognitive science have dominated the discussion. A central theme running through much of this work is the question: what kind of machine is the mind? A widespread assumption in cognitive science is that the mind is a mechanism, a physical system with distinct parts that perform specific functions. The task then falls to psychology to figure out the details. What are these parts? How do they operate? And how does the whole thing develop? A hugely influential answer to what kind of machine is it has been: the mind is a computer. According to this view, processes like seeing, thinking, and remembering are essentially computational processes. This idea has taken many forms, but two dominant approaches are classical computationalism and connectionism. Classical computationalism has deep roots, heavily influenced by figures like Alan Turing. At its heart is the idea that the mind is like a symbol manipulator. It works with internal representations, symbols, that have both meaning semantics and structure syntax. Think of it like a language of thought. The core claims are: first, we manipulate mental symbols with meaning. Second, our cognitive processes only care about the structure of these symbols, not their meaning. Syntax matters, semantics doesn't directly drive computation. Third, these processes are algorithmic, following step-by-step procedures guaranteed to produce a result. This view implies that having a thought is just having the right computational relationship with the right symbolic representation. Why was this view so popular? Advocates highlighted its explanatory power. One big selling point is explaining rational causation. When we reason, say, from all men are mortal, and I am a man to I am mortal, the earlier beliefs cause the later one, and their meanings logically entail it. Classicism sidesteps the homunculus regress by saying inference follows formal rules applied to syntax, not direct semantic influence. Since the process is algorithmic, no inner interpreter is needed. Another major virtue is explaining productivity and systematicity. We can think novel thoughts, and if we can think one thought, we can usually think related ones. Classicism explains this elegantly. A combinatorial system allows combining basic elements into infinitely many structures, and the same rules generate related structures. But classicism faced powerful objections. John Searle's Chinese room argument is a classic. Imagine someone in a room following instructions to manipulate Chinese symbols, producing correct answers to questions they don't understand. Searle argues this shows syntax manipulation isn't enough for semantics or understanding. Classicists respond they never claimed syntax equals semantics. They claim thinking is computation on representations that have semantics. Searle's conclusion doesn't necessarily contradict this. More empirically oriented objections point to the frame problem. How do we efficiently determine what information is relevant for tasks like planning? A classical system would need to check everything, which is computationally nightmarish. Finding a computationally feasible way to handle relevance seems difficult to specify classically. These challenges fueled interest in alternatives, chief among them connectionism. Inspired by neural networks, connectionism models cognition as a network of simple processing units connected by weighted links. Information flows through these networks, typically from input to output layers, with connection weights adjusted by learning algorithms. These models have proven remarkably successful in simulating various cognitive abilities. Interestingly, many connectionist models still operate within a computational framework, sharing assumptions about representation and algorithms with classicism. The key difference lies in representation. Connectionist representations are typically not structured syntactically. They reject the classical idea that cognition fundamentally operates on symbolic structures with formal rules. Connectionism boasts its own set of virtues. Proponents highlight speed due to parallel processing, graceful degradation meaning the network still works reasonably well, even with damaged parts, a certain neural realism, impressive learning capabilities, and good handling of problems with many conflicting constraints. Critics counter that some virtues aren't unique to connectionism, and the neural realism is debatable. More significantly, connectionism faces its own objections. Fodor and Pilishin argued it struggles to explain systematicity and productivity. Gary Marcus pointed out difficulties in representing individuals versus categories. And like classicism, connectionism hasn't provided a compelling solution to the frame problem, especially for complex reasoning tasks. Given the strengths and weaknesses of both classicism and connectionism, many researchers now favor hybrid models. These propose combining the best features of both, perhaps using classical architectures for high-level reasoning and connectionist mechanisms for more associative or perceptual tasks. Beyond these computational frameworks, there are even more radical alternatives, like dynamical systems theory, which views cognition as arising from continuous dynamical systems, described by equations similar to those in physics, rather than discrete computations. Evaluating these diverse proposals remains a vibrant area of research in the philosophy of psychology. Moving beyond the micro-level details of computation, we ask about the mind's overall architecture. Historically, we talked about faculties. Now we often speak of cognitive systems. A major debate concerns modularity. To what extent is the mind made up of specialized, relatively independent modules? Think of modules as dedicated autonomous systems for specific jobs, like vision or language. Non-modular systems, in contrast, are more flexible general-purpose processors. The debate ranges from minds being just one or a few general-purpose computers to minds being composed of thousands of highly specialized devices. Most likely, the truth lies somewhere in between. Jerry Fodor famously argued for a specific kind of modularity. He proposed that modularity is mainly found at the periphery, input systems like vision and language perception, and output systems like motor control. Central systems responsible for reasoning and decision-making, he argued, are non-modular, domain general, and informationally unencapsulated, meaning they can draw on information from anywhere. Fodor characterized modules by a cluster of features: domain-specific, encapsulated, fast, mandatory, shallow, neurally localized, etc. The core ideas are domain specificity and informational encapsulation. Central systems, by contrast, combine inputs from different domains and aren't constrained by encapsulation. Fodor's view, however, has been challenged. Massive modularity proponents accept input-output modularity but argue that central systems are also largely modular. They suggest we might have specialized modules for things like social reasoning, understanding biological categories, or probabilistic judgment. Carruthers offers a task specificity argument. Since different cognitive tasks like vision, speech recognition, grammar induction demand different things, we need specialized mechanisms for each. But critics argue this doesn't fully rule out alternatives. Maybe we have unspecialized inference mechanisms that use different bodies of specialized knowledge for different tasks, rather than having separate inference engines. The argument doesn't clearly distinguish M from this possibility. Furthermore, radical massive modularity struggles to account for certain aspects of cognition. We seem capable of freely combining concepts across domains, like thinking about red, round, tasty apples. We can deploy these integrated thoughts in deliberation, assessing their truth or relevance. And relevance itself seems highly contextual. Inferential holism, almost any belief can be relevant depending on background assumptions. These phenomena seem hard to capture if central cognition is entirely modular. A more plausible approach, perhaps, is a dual systems account, where central processes involve both modular and non-modular components, aiming to capture both specialization and flexibility. Another fundamental question about the mind concerns its origins. How much of our mental structure is innate? This pits nativists against non-nativists, often empiricists. Nativists argue the mind comes equipped with substantial innate structure, concepts, knowledge, mechanisms, modules. Empiricists claim the mind starts relatively blank, possessing only basic perceptual systems and general learning mechanisms. The debate rages across many domains, but nowhere more intensely than in linguistics, largely due to Chomsky's influence. Humans reliably acquire complex language skills, suggesting shared innate resources. The poverty of the stimulus argument, POSE, is central. The linguistic data children encounter is insufficient for an empiricist learner to acquire the full grammar, implying innate linguistic knowledge or biases are necessary. The POSA faces challenges. Critics question the assumption that negative evidence is scarce, arguing children might receive or use it. While traditional behaviorist empiricism is clearly inadequate, recent advances in statistical learning might provide a better empiricist account. However, Even successful statistical models often rely on assumptions about the structure of linguistic input, which could still be seen as a form of innate bias or a specialized learning module. Complicating matters further is the very concept of innateness itself. Is it simply being present at birth, or solely genetically determined? These definitions seem problematic. Philosophers have suggested refinements, like traits that are environmentally canalized or psychologically primitive, but the debate over what innateness truly means continues. So, whether we're exploring the quantum realm or the intricacies of the mind, we find ourselves grappling with profound questions about reality, explanation, and the very structure of our understanding. From the wave-particle duality and the measurement problem to debates about computation, modularity, and innateness, the quest for a complete and coherent picture remains ongoing. These foundational issues continue to challenge and inspire research across both physics and psychology.